Well, hello again. In this video, what we're going to do is we're going to examine the continuity of a function. And in this particular example, we have this rational expression, a linear function up in the numerator and a quadratic function in the denominator. Now, before we go ahead and get into any algebra or calculus or any kind of mechanical manipulation, I like to look at a graph to give me a general idea of what it looks like. Okay, so here's the graph of the function. I've just entered it into my calculator. I've actually changed the window, and I'm actually going to change that to a -4 instead. So I have a normal 10 by 10 window, except my x min is now -4. And so here it is. Okay, it appears that we have this vertical asymptote right here. And if I just looked at this graph from the calculator, and I wanted to talk about the continuity of this thing, I might say that it's continuous everywhere with the exception of 5. It looks like we have a vertical asymptote at 5. In other words, if I were to trace this graph, I would trace my pencil along the curve, and the only place I would have to pick it up would be right at 5 to continue up here. Okay, that's what the graph gives me. So I can expect most likely a discontinuity at 5. Okay, but as in previous examples, you need to be careful with the calculator. The resolution is not very good. There could be some other discontinuities in here that we just don't know about. So the first thing I usually try to do is I try to examine the domain of my graph. Usually when you get a discontinuity, it's because of I don't want to say usually, but sometimes it can be because of a domain violation. Okay, so if I factor my denominator here, this will give me a better idea of what the domain of my function is. And I believe the denominator factors to x minus 5 times x plus 2. Okay, so this is my new function. Now, what's the domain of this function? Well, I know that I can't plug in 5. That's probably where that vertical asymptote is going to come in. But look what else. Notice that -2 is also not in the domain of this function. Okay, it doesn't get mapped anywhere. Okay, so -2 appears to be perhaps another place of discontinuity. Okay, well if we go back to the graph, we really can't see that in here. -2 is right here. In fact, our graph doesn't even show up. So what I'm going to do, I just want to see if my calculator will pick this up. And I'm going to go to zoom box, and I just want to zoom in on the area around -2 to see if I can't see perhaps a little hole or maybe some other kind of discontinuity. Okay, and there we go. So I've just put a little box around -2, and let's see what that gives me. Okay, well here's -2 right here, and you can see that it goes through. There's no hole there. Okay, but that doesn't mean anything. Remember the way your calculator graphs is it plots some points and then it connects the dots. If it never plotted -2, it may think that -2 is in that domain. So I don't know if this next thing is actually going to work or not. I'm going to do a zoom decimal, and that's going to ensure that my calculator actually plots -2. And look at that right there. You can just barely see it. Okay, you can see this little hole right there. In fact, if I turn off my axes, you might be able to see it a little bit better. Okay, there it is right there. We've ensured that we've plotted -2, and sure enough, a hole came up. So once again, as I'm tracing this graph, I physically have to lift my pencil up, cross -2, and then continue to retrace my function. So I definitely have another discontinuity at -2. Okay, now the algebra behind this is pretty straightforward. You can see that if I remove this factor, okay, I cancel this factor out. This is how I remember that this that we're going to have a removable discontinuity at -2 because we've sort of removed this factor. That's how I remember it. Now, if I rewrite the new function, I have 1 over x minus 5. Okay, so here's my new function that if I graph this guy in this guy, they would be identical functions. In other words, I'm not going to do it on the calculator, but we saw before that at 5, this was 5 right here, we had this vertical asymptote. Okay, and then it did something like this, and then it did something like this. Okay. Now, upon careful inspection, though, at -2, we saw that there was a little hole right at -2, right about right there. There's a hole. Now, if I graph this guy, I would get this identical graph, except for the hole. Okay, so these two graphs right here agree with each other at every single point, with the exception of -2. Okay, so remember that we want to talk about the continuity of this function, not of this function. This just helps me see that at -2, I'm going to have a hole. It's been removed. That's my removable discontinuity. And at +5, I'm going to get that asymptote, that vertical asymptote, and that's going to be my non-removable discontinuity. So how do we write this? Well, we can say that f is continuous on some intervals here. Well, what are the intervals? We start from -infinity and we run to the right until I first have to pick up my pencil, which occurs right here at -2. This is, I guess I should write that, -2. So from -infinity to -2, and it doesn't include -2. Remember, -2 is not even in the domain of this function. So it makes sense that it wouldn't even come into the discussion of continuity here. Unioned with -2, well, let's see where we pick our pencil up again. We continue to trace until we get to 5, and we jump over 5, and we run out to +infinity. Okay, again, I want to stress that at 5 we have a non-removable discontinuity. At -2 we have a removable discontinuity, and these are the intervals over which the function is continuous. Okay, I hope that made sense. Thanks for watching.